Okay, good afternoon, everyone. Thank you for coming to the very last session of the day. I appreciate it. I'm always worried when I'm the last session, like how many people are actually going to show up. So thank you. Thank you for being here. So what I want to do is, I have a proposition that says, look, we've been building storage systems, network storage systems a certain way using general purpose processors, but we want to tell you about the DPU and the fungible DPU and why we think it's a really, really good ASIC for building, network storage. And I want to take you through the advantages, performance, power, and other things that I want to walk you through. And, hopefully convince you that in fact, this is something that actually makes a lot of sense to start building storage systems using DPUs. So before I do that, I have to give you a little bit of a DPU introduction, particularly because, there's a certain model of what is a DPU out there. And I kind of want to reshape your head just a little bit about what that DPU is. And I want to go a little bit into this fungible DPU. Particularly, we've built two models of the DPU, and I want to take you through one of them, which is the one we use to build our own network storage product. I want to show you why it's a really good processor for building storage systems. And then I want to walk you through we've actually built one of these things. We've actually built a storage system that only uses a DPU. There is no general purpose processor inside this box. Inside this cluster, many boxes, you can cluster it. It's a scale-out storage system. There's no x86, no ARM, no general purpose processor in it. So that's a proof point. You can build it. This is a product that we've had in the market for 2 years now. It's like a 4th generation product. It's mature. People are running production environments on it. So this is not a toy. It's not something, hey, I built a prototype. No, this is a product. People are running real workloads, on it. Then I want to take you through some comparisons, sort of architecturally, just make some arguments about why, what are some of the benefits of building this kind of thing. By the way, I'm not very good at terminology, so DPU-based storage, I'm going to keep calling it DBS on this talk, and then CPU-based storage, CBS. Okay, so I'll often make these comparisons, but CBS is the traditional way we all know. I mean, I've been building storage for a long time. I won't tell you how long because that'll age me, but I've been building storage at IBM, at Dell, at many places along the way. And this is the first implementation of DBS. So I kind of want to take you through CBS versus DBS. So one is I'll make arguments, but then we've actually built this thing. So we can show you measurements on the real product, compare it to real measurements on CPU-based storage systems. So hopefully at the end of this, enough of you in this room will go away thinking, yeah, this is a really interesting way to build storage systems of the future. And while we've built our own, we welcome others that are interested in using the DPU to build their own storage systems. That would be a good outcome for us. I mean, we make chips, we make DPUs, we make storage systems. But if other people want to use the DPU, we'd be open to having a discussion. Okay, so that's the flow of the talk. So quick introduction to DPUs. Really DPUs came about for two reasons. There's two mega trends happening in the industry. One is more and more of activity and tasks inside data centers are what we call data-centric. By data-centric, we mean high bandwidth streams, multiplexed, many streams. So when you build a storage box, you've got thousands of volumes open, lots of QDEP, num jobs, lots of stuff in parallel that's happening. Networks are that way. The way you do security is that way. So there's a lot more of this. And as bandwidths improve, storage is getting faster, networks are getting faster. I mean, all our customers are moving to 400 gig TORs. There's more and more of this activity. And general purpose processors are not great at this. I think everyone knows that. So more and more of the cores of servers are actually being deployed in doing infrastructure stuff, and really is not the best way to use those cores. We really should be using them to run customer applications. So part of the rise of DPUs is because of that. The second reason is, everybody wants to build their data centers more and more like the hyperscaler data centers. Cloudify, if you will, as a term, cloudification. And for that, you need to disaggregate. Disaggregation is a good way to improve TCO. You need good data center networking. DPUs are good at that as well. So those are the two driving forces for DPUs. Now, I'm sure most of you have seen a chart like this or know enough about DPUs to know that, DPUs have compute cores, they have accelerators, they're programmable. I think some of you were at the previous talk. You write code in C. They're but they're very tailored to do data-centric tasks, and they communicate, PCIe to SSDs or PCIe to hosts, and of course you have network ports on the other side. So there's just two ways that these things communicate to the outside world. But inside it, you've got compute cores, you've got accelerators. And they're really good at these data-centric tasks, and we'll talk a little bit about that. And our own personal view is that there will be more and more DPUs in data centers. There are CPUs today, there are GPUs today. We think there will be more and more DPUs because there's more and more data-centric tasks, right? Now here's where I want to make a little bit of a difference from maybe other DPU-based talks that you've heard about. There's sort of two classes of DPU-based products in the industry. And in fact, if you were at the previous talk, that's an example of a product on the left. It's a DPU that's ancillary to a server, to a general purpose server. It offloads tasks from that server. And we had a very nice talk about running a storage initiator as an example of offloading NVMe TCP driver and not running it on cores and moving it onto the card. We've also built switching and routing functions. The particular box card we built, could save you 7 cores. It could improve latency a lot, could improve throughput a lot. So there's one set of products is on the left. I think most people, when they think DPU, think the products on the left. They think SmartNIC, they think, I want to offload something from my server. It's a great use case, but I want to talk about the other use case. I want to talk about the use case on the right, which is you can also build certain kinds of products where the DPU is the only processor. It's not ancillary to anything. It is the processor. So we've built a storage box in which the DPU is the processor, right? So I really want to talk about the products on the right. Nothing against the products on the left, but that's what everybody talks about. So I kind of want to give you a little bit of a different spin and talk about the products on the right. So I'll talk about our high performance storage product and how we used a DPU to build it. So we have built two kinds of DPUs. I'll call it the small one and the big one, just to keep it simple. The small one is the one that goes on these offload cards. The big one is the one that goes inside our storage box, okay? So what's so special about this thing? Why do we think it's really ideal for building storage? So a few things, and mostly I'll focus on, it's either pink or purple, and I can't tell, but that color bullet. So on the networking front, very efficient TCP. We've built very efficient TCP with the DPU. I think it takes like only one core and can do 100 gigabits per second. We do have this thing called True Fabric. I won't talk too much about it, but the True Fabric is something that really can avoid congestion in the data center network. Those are all important to building storage, to building network storage, right? Networking is important for network storage. A couple of things on the compute side. The way everything works inside our DPUs, it's all run to completion. Everything is you're just scheduling these run to completion handlers. So really there are no interrupts. And that gives you, and I'll show this when I show you some of the tail latency performance numbers of our storage box. You get very, very good tail latencies as a result of this kind of model, because you don't have interrupts. You can more precisely see how long things take and how bad things can be. I think there's an important reason why we have some very good tail latency numbers. I'll skip the PCIe part. Few points on the specialized memory systems. Storage systems put a lot of stress on DRAM inside the storage box, and our package includes some HBM, and I'll show you some of the benefits of using HBM to build storage systems. I think it's important to get high performance. The other thing is we do have different kinds of memory, so buffer memory versus memory for state and so forth. We can avoid cache pollution by keeping things separate. When data is flowing through, you put them in the buffer memory. State is in a different kind of memory. One doesn't pollute the other. And then finally, we've got a lot of the kind of accelerators that you need for storage. We've got erasure coding for Reed-Solomon type acceleration. We have compression, very good compression, encryption, etc. And I think the important part here, and I think Pratapa mentioned this in the last talk, it's very fast to access these things. You could be running a piece of code in a core. 40 nanoseconds later, you're using some compression hardware. You can come back to the core, go back to hardware. So, as you guys know, if there's a lot of overhead to go use an accelerator, then you don't want to use it for little things. But when it's so fast to go use these things, you can use it a lot more. And I think that's a key part of why we get the performance we get. So those are some of the aspects. Otherwise, it looks like a DPU. It's got a lot of threads, 192 threads on our chip. You've got connectivity to PCIe. You got 64 PCIe lanes on this big DPU. You got 800 gigs of bandwidth, a lot of bandwidth to networking. To do the equivalent on a general purpose processor, you'd have to put 800 gig NICs, or you'd have to put 4 dual ported 200 gig NICs, but it's all there. It's a little piece of the corner of the chip. Yeah. We have 2 channels. Okay, so and I just want to share with you, this big chip, the F1 DPU. Just look at the bandwidths of some of these accelerators. These are just, really. We're trying to match 800 gigs per second, so most of these things can run at line rate. You do compression, you're doing compression at line rate. You do encryption, you're doing encryption at line rate. So, unlike a lot of storage systems, people just feel free to turn on compression. People feel free to turn on encryption because it doesn't slow you down at all. I'll show you some numbers. And that's because these things are so fast. So they go very fast. What is the what? That is our hash table lookup. Yeah.
So what does that mean?
Sorry.
So what does that mean? What is the hash table lookup?
So if you have data structures that need where you do hash and then do a lookup, so this thing will accelerate those kinds of hardware assisted hash table. Yeah, good way to think of it. Yeah, thank you. Okay, just one quick slide on software. Pratapa actually talked about this in the last presentation. We have a very high performance programmable path, right? So you got the host engine, that's the PCIe side on the left. You've got the networking stuff on the right. All those little circles, think of them as cores or threads. Think of those squares as our hardware accelerators. We've got 7 or 8 different kinds of accelerators, but each of the accelerators are also multi-threaded. That's why you see squares of the same color, more than one square of the same color, because I got lots of compression engines, threads, a lot of encryption threads, and so on. And then very high speed, on-chip network. It's like 20 terabits per second. You can do lots of call continue, so you could be executing something on one of those blue circles, and then you can call one of these hardware threads. Up at the top of the picture, you'll see kind of like a data flow. We talk about these execution pipelines. You can go from, a blue circle to a green square, and then back to another blue circle. Eventually, you work your way out, but it's all run to completion model. And I think that'll help our performance, as you'll see here in a minute. Okay, so now I want to just start comparing building storage systems with general purpose processors versus building storage systems with this kind of ASIC, this kind of fungible DPU, programmable processor. So typical, not meant to be, it's just a general diagram. I mean, I've built lots of storage systems that look like this. You've got, 2 general purpose processors. You got some NICs. Some people use accelerators. Some people just use the x86 to do some of the acceleration. It's just, general diagram. You've got some DIMMs for memory. You might or might not need more PCIe switching, depending on how many SSDs you want to connect to. It's a general sort of picture of how something looks. And what I want to share with you is, so the traditional way is the picture on the left. I show x86, but a general purpose core of some sort. You've got accelerators potentially sitting in PCIe slots. You've got NICs of some number of NICs. And then, of course, externally, you have DRAM. So the evolution that we are seeing is that almost everything there except the DRAM is actually on our chip, right? All the NICs, I got the equivalent of 8 NICs inside a little corner of that chip. I've got all the accelerators you want inside that chip. I've got all the cores you want inside that chip. So instead of a set of discrete parts, we're really giving you all the things you need to build a storage system inside that chip. We even have high bandwidth memory on the chip, which we'll talk a little bit more about. Of course, DRAM is not on the chip. You have to go out. So just like that. But I'll walk you through, why this is lower cost, lower power, higher reliability, a lot fewer pins, in this design on the right versus the design on the left, and the performance. So I'm going to walk you through all those things. Now, I also want to just, I'm going to give you, real numbers for all these things, but here's a sort of a word chart on, like, why do we like using the fungible DPU? If you think about a storage workload, it has some very special requirements. You're handling tens of thousands of concurrent streams of data, and general purpose CPUs typically have low IPC when you have these multiplexed kinds of workloads. DPUs are also very good at, terminating stuff, whether it's PCIe, TLP termination, or, network termination. Third one is you typically have to do multiple passes through the data. Data comes in, you compress the data, you stick it in memory, then you pull it out, then you encrypt it, you put it back into memory, read it out again, do some erasure coding, put it back into memory. There's a lot of stress on the memory bandwidth. So that's an issue that we can resolve with the fungible DPU. We do have this notion of separating buffers and state and not having one cause cache pollution. That's an important advantage. And when you're building storage, it's good to have accelerators for data reduction, for security, encryption, protection, and we have all that. So those are sort of 5 high-level reasons why we like what we have done, and why by the end of this talk, I hope more of you will like and think about building storage using this kind of DPU. So now, like I said, we've built a real product. It's been out in the market for 2 years. It's in its 4th generation, so I want to tell you a little bit about it. Those of you that went to just Paul's talk probably heard some of it in that talk. But this is the world's first, DBS, DPU-based storage implementation. So the boxes that we built are these boxes on the right of the picture. Each of them is a 2U box with 24 SSDs inside of them. And it's a scale-out design, so you can start with, let's say, 3 of these boxes, and then keep adding more. And then, of course, on the left of the picture, I show you the servers with standard drivers, vanilla NICs. Of course, Pratapa talked about how if you use the storage initiator, you can get even better performance. But all the numbers I'm going to show you here today, just using standard NICs. No, nothing special, not using the initiator that he talked about. And of course, we're doing NVMe over TCP. Now, there's like 5 bullets here, as you can see. I'll talk about performance. It's very high performance. A single box can do up to 13 million IOPS. I mean, when I was doing x86-based storage, which I have done a few times, it's very hard to get to 1 million, right? I mean, 13 million is like a really nice, good number. And you'll see the latencies. I think somebody asked in the last talk, we are adding, less than 10 microseconds to the SSD. If that's 110 microsecond SSD, I'll show you our latencies. They're very, very good. End-to-end latencies, I'll show you that. It's a scale-out design, so you can keep adding nodes. We take care of all of that. It's really a full function. It's a full function storage product. It does all the things you might expect: compression, thin provisioning, snapshots, clones. We have quality of service. And all of these things we provide to you on a per volume basis or a namespace basis, whatever terminology you like. So you can say, hey, I want this volume to have compression. I want this other one to be protected with 4+2 erasure coding. I want this one replicated. I want this other volume. I don't care because I got software that takes care of replication for me. So just give it to me raw. So all of that, very fine-grained at a per volume basis. So it's not, a lot of storage systems will just say, well, all your data is compressed, or all of your data is 24+2 protected, or something like that. In our case, it's very, very granular. I mean, it really follows the elastic block storage model of Amazon. You've got different kinds of workloads. Each workload has a different need. You come in and say what you want, say what quality of service you want, and we give you what you want. So that's the third point. Where's the fourth point? It's very, very low power. That box is 750 watts. A typical box like that with 24 SSDs using general purpose processors will be about 1,500 watts, maybe even more. So this is about half. And by the way, 600 watts of that is just SSDs. I can't save any power on the SSDs. So if I take the SSDs out, then my power advantage is, very, very significant. But even with 600 watts of SSDs, I'll give you 750 watts in that 2U versus 1,500 watts typically. And then, of course, it's, like I said, built entirely with DPUs. And then we do this rack level protection. So this is also quite differentiated. I mean, whether you go to Amazon, EBS, or Azure, they all use, typically for high performance storage volumes, if you want protection at the node level or you want protection at the rack level, you have to do like 3-way replication or something like that. In our case, we do 4+2 erasure coding or 8+2 erasure coding. Actually, we can do M+N erasure coding. There's only so many things that we have done QA on in the product itself. So those boxes can be in different racks. So you can do 6 racks. You can do 4+2, and any 2 racks can go down, and we're protected. So it's as good or better than 3-way replication. But this is possible to do because of the DPU, because you've got very efficient networking, you got the support for the erasure coding in the DPU, and that's why people typically don't do EC today. They'll do EC within the box, of course. Yeah, everybody does EC within the box. I'm talking about networked EC, which is hard to do. But you need to do if you're trying to go into a data center that's got thousands of racks, you have to deal with rack failure, you have to do this kind of thing. We do it with erasure coding. So this is just showing you that there really is no general purpose processor. It's just a picture of the board. This is the board that's actually inside our real product. It's actually an older version of the board, but you can see all it's got is it's got the 2 DPUs, it's got some RDIMMs and some NVDIMMs, it's got a BMC, and then you got the, SSDs on the right, 24 SSDs on the right, and then you've got all the network connectivity on the left. And this is just, I just wanted to show you, it's a real board. There's nothing in it. There's no general purpose processor in there. So I want to show you some performance numbers now. Like I said, we have 3 modes. Actually, we have more than 3, but I think for the purposes of this talk, we can give you raw volumes, which says, I don't do any protection for you. It's your problem. Your software takes care of it. Often if you're running MySQL or something like that, they do replication in software. That's fine. We can do protection for you. For example, this is RF equals 2 protection. And then we can do erasure coding for you. So this is the 3rd row is, with 4+2 erasure coding. 6 nodes, 4+2 erasure coded. And you can see the numbers, 15 million IOPS per box for raw. With network protection, you're getting 15 million across 2 boxes, or that's about 7.5 million per box. And then, you can see the numbers for erasure coding. This has been, this is scaling. I mean, the product we ship today goes up to 16 nodes, but I think you heard Jaspal's talk. The architecture will support scaling, and we don't envision any problems beyond that. No impact to performance typically when you turn encryption on or performance or compression on. And I'll show you some numbers, databases where you have local SSDs. I take the exact same SSD that's inside our network storage box. I take that same exact SSD and stick it inside the server, and I'll show you a comparison of what happens if you have the exact same SSD local versus the same SSD sitting over the network inside our DPU-based 2U unit. And I'll show you real numbers. So, and then, even the bandwidth numbers, I mean, I'm sort of running over, there's a lot of performance data on this chart. I mean, that's 75 gigabytes per second from 1 2U box. I mean, that is just a lot of performance, right? Now, some quick numbers on latency. I wanted to show you some latency numbers where basically I'm running this thing at peak max IOPS. I'm running max IOPS. You can see our average latencies are still numbers like 400 microseconds, 200 microseconds, 178 microseconds. So the latency this is not like with, num jobs equals 1, Q depth equals 1. A lot of people will just give you that number. This is not that. This is like I'm banging the box, max IOPS, whatever it can do, and I'm still giving you, really low latencies. And even the 99th percentile latency at max IOPS is approximately a millisecond for read, and it's 369 microseconds for writes. So this is my point about, I think some of this comes from the DPU, the way the software is written, and all of that, right? So here's the performance with MySQL, and this is, I'm sure some of this is hard to read in the back. I've been in the audience for the last 2 days, and I noticed that a lot of charts are very hard to read in the back. So I am sympathetic to people in the back and not being able to read stuff, but very easy to read this chart. The lower is better, and the orange color is going over the network, and the blue is with local SSDs sitting inside the server, and it's the same exact make of SSD. You just pulled it out of that box and stuck it on the server. In this particular case, there are some reasons for why we can even be better. Some of that has to do with the fact that when you're running MySQL, typically you turn compression on in the software. I've turned that off, and I'm doing compression with my DPU. So there's some reasons for why I can be even better in some cases. Also, of course, we have NVDIMM, so we can do fast write, and so I can tell you your write is done very quickly. So all of those things kind of factor into play here. This is not something that people typically do today in standard block NVMe storage boxes, but I mean, this whole conference has been talking so much about computational storage. There's so much momentum around that stuff. I just wanted to show you, one particular, this is one where we've had a lot of customers that are interested in just doing regex searching. People have lots of logs. I mean, every piece of software in the world seems to create logs, and people want to go keep that stuff around forever and want to go searching on these things. So we're finding interesting customer-driven use cases. So I just showed you the regex example. I could have shown you TPCH or some of the other things, but the hardware DPU does have a regex engine in it, and compared to software, which is the dark blue, you can get a factor of 10 faster regex searching, and it really doesn't matter much. The complexity of the regex search that you're doing doesn't really impact performance very much. What does impact somewhat is like how often the pattern you're looking for appears in the data that you're searching through. But very good performance there. So now we've built this thing. So now I just want to give you some results from actual customer studies. First, a little bit of why we are better, and then I'll show you a real example. So first, efficiency. We do erasure coding. Erasure coding overhead is like, if you do 8 plus 2, that's just 25% overhead. You could do 30 plus 2. Actually, our chip supports up to 32 plus 8. That overhead can come way down compared to doing three-way replication. Also, the compression. The guys that built the compression hardware, it was like their 4th generation of doing compression. They've been at other companies that have built compression hardware. So there's just some stuff that they were able to do. And this is customers telling us, hey, the other guy's compression gives 2.5x on my data, but your compression is a little bit better. And that's what we've found. Actually, our compression is as good as Google's Broadly. But Google Broadly, you can't really put into hardware. It's really something that takes a long time. So we're about 100 times faster than Google Broadly because we're doing it in hardware, but it's about the same level of compressibility. What's that? We have different kinds of compression. We have LZMA, we have gzip, and there's a third type of compression we use as well on JPEG images. But yeah, okay. Sorry, I've forgotten to repeat questions. I'm sure that's a problem. But anyway, so now here's a real customer, and I've normalized things to, they wanted to store a petabyte. How many raw terabytes do they need to buy to store a petabyte? And they were doing direct attached storage, so they were not even using network storage. They just used local DAS, and they did three-way replication. So that's the leftmost 2 columns, and then the middle 2 columns is us, and then the rightmost 2 columns is another competitor that they were looking at. And I'll just focus you on the very last row. So the way they were doing things, to get effective 1 petabyte, they needed 5 petabytes of sort of raw because of the three-way replication, et cetera, and the kind of utilization that you get. And then with us, they're about 500 terabytes. And then with the competitive box, it was 1.5. Again, it was RF, the others were using RF3 to get 2 failure protection. Their compression was not quite as good, et cetera. So that's the cost stuff. Now, power is another really, really important point. Again, I actually use numbers from one of our customers who said, hey, this is the alternative I'm looking at. I'm using an Intel dual socket Ice Lake server. I'm going to run some software-defined storage thing on it. So I just made a comparison of us versus them. You can see that, I think I mentioned this, with 24 SSDs, we're about half the power, 1500 versus 750. If you don't include the SSDs, we're about 4.4x better. But I think the important one is the box at the top. One of our customers has 2 exabytes of storage, so that might be like 10,000 storage boxes. Now, we have not won all 10,000 boxes from this customer. I hope we do someday, but they do have 2 exabytes, and they have some of our boxes. So I just did some math, and I said, what if I could get every one of those boxes to change from what they're doing to use our box instead. And that's, you can save 54,000 megawatt hours, and you can do the math. We could save them $3 million a year. So this equation, is factoring a lot in our discussions with customers. This is a big deal, right? I mean, saving somebody $3 million a year is a big deal. So we think this is important. And then from a rack space point of view, again, this is a real customer example. We can do the same thing with 1/5 as many racks, essentially, or rack units, if you will. And again, this is a combination of our power advantage, because this customer has 12 kilowatt racks, so there's only so much you can put in a rack before you go to the next rack, and so on. So that's that. Okay. Then the last thing is on performance, and this is the point I was trying to make earlier, that storage systems really, really stress out the memory systems on servers. So you go into memory, you bring it out, you compress it, you go to memory, bring it back out, encrypt it, and so on. There's at least a factor of 6 compared to the bandwidth coming off of the SSDs. So, there's a lot of SSD manufacturers here at this conference, and I'm sure many in this room. Already Gen 5 SSDs are here. If I want to support 32 Gen 5 SSDs, and even if I assume I don't use all 4 PCIe lanes and do by 2 bifurcation, that's still 2 terabits a second of bandwidth that's coming off of the SSDs. And as a storage system builder, I don't want to be in the way. I want to be able to take what you're building and give it to the application. So I want the same 2 terabits per second to flow back out to the host system. Well, that means I need 12 terabits per second of memory bandwidth, just doing the 6x multiplier, right? And you just don't have it. I mean, this is an AMD EPYC 3 machine that had a monstrous number of PCIe lanes, but I'm still stuck with not having enough to support that, which means you won't support 2 terabits a second. You might end up supporting half a terabit per second or something. Whereas if you use the DPU and the ASIC, you could continue to keep up with these new things that SSD manufacturers are continuing to build. So, performance, I have some performance comparisons here. Performance comparisons are really hard to make, as you guys know, right? I mean, it depends upon how beefy of a server you use when you look at CBS, the CPU-based storage versus DPU-based storage. Are you using the same protocols? There's just a lot of things that go into it. I've tried to be as fair as I know how to be in making these comparisons and not over-claiming a lot of stuff. But nonetheless, just looking at real numbers from real products, whatever we're able to see, we believe that the DPU-based things can give you anywhere from 3 to 8x better performance as well. So, to sum it all up, this is really my summary chart. The left is the way we've all been used to building storage. I want all of you to hopefully have opened your mind a little bit to say, look, there is potentially a new way to build storage, maybe using this kind of DPU on the right. And then I just, summarized like all of the different attributes: performance per watt, power, rack space, storage efficiency, all of that stuff, and said, look, there is significant benefit, and I hope after this talk, more of you will at least give it some consideration. We've built the first DPU-based storage. We're talking to some others. I'm hoping that some others will also do, and I think for us it'll be a success if more people start to see this and start to see the value and start to move in this direction. So I think that's my last chart, other than pointing out that if you missed Jaspal's talk, make sure you go look it up. He gave a nice talk on Monday, more about the architecture. How did we achieve these numbers? What did we have to do? How did we separate the control plane and the data plane? And then I know many of you, at least half of you, were here for Prathapa's talk on the storage initiator. So with that, I will stop and take any questions. Yeah?
I have one question. The typical storage set, right, have some, what do you call it, like, 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 like,
The F1 has 48 cores, 192 threads.
But you use that for some of the data, right?
Use some.
But here, for this like general purpose, like F1 processing.
You're talking about background processing. Yeah, we use the same. We have plenty of cores. I mean, you saw our performance numbers. Usually, our problem is the other way, right? I mean, a lot of customers will say, do I need that level of performance? I mean, I can afford to not use some of those cores, and and there's a lot of the cores in the CPU have never been a problem. We do all the things that standard storage boxes do. We do background checking. We do all of those kinds of things. We have CRC. The data comes in. We add the CRC to it before it goes back to the host. We check the CRC. We strip the CRC. We give stuff back. I mean, we do all the things that standard storage boxes do with what we have here. So. So we have an SDK for people that want to build, say, storage systems using this DPU. We have an SDK that can be used. We don't. I mean, it's not like it's something a lot of people can start using it, but for people that are really, really serious and want to talk to us about it, we can provide an SDK. Inside the box, I think Pratapa mentioned this, we really have two operating systems inside the box. For a lot of the data plane stuff, we've built this run to completion operating system, which we call FunOS. And we also have Linux, of course, in the box primarily for control plane stuff. So all of those APIs that you saw in some of his pictures, all of that, is implemented on Linux. So we have both. So I hope I answered your question, but okay.
SPDK also does a sort of run to completion.
Yeah.
That's that too. So I could run SPDK on Linux on your box and get similar without no interrupts and so forth like that. So.
Yeah, I think, and I'll let the software experts here, also answer the question, but I think that to really get the kind of performance we're talking, so I don't think you can just take general purpose software and just port it over and expect this kind of performance. I think you do have to custom build.
I understand that.
Yeah, you have to use these accelerators and so forth. And I think, that's sort of our, what we have had to do, Jaspal, Pratapa, these guys that have really built the software, that's what they've had to do to really get this level of performance. So you'll get some performance if you do what you're suggesting. I just think it will not be anywhere close to this. Do you want to comment, Jaspal, anymore? Or?
My point here is that with all the talks about the DPU, one of the primary things that they mentioned is that the DPU is programmable. Yes, your DPU is programmable, but it looks like you're the ones doing the programming.
So I just want to know. Let me answer that one. We have customers that have programmed the DPU. We have customers that had their own storage stack that was running at performance X, and then after a month and a half of them programming the DPU, they got that performance to go from 1x to 6x. So no, we're not the only ones programming the DPU. There are others programming the DPU, and it's not taken them very long to take something they had and make it run 5-6 times faster.
You seem to downplay the SDK. That's all I'm saying.
No. I mean, I think that that's how that SDK was used by this other customer to.
That's great.
Yeah,
happy to
yeah,
hear
yeah,
that.
yeah, yeah.
It's just when you first mentioned it, it seemed like you downplayed it. That's
Okay, yeah, yeah. I mean, to be honest, I mean, it's not like, it's not like where the SDK is in a place where come, hundreds of customers can start. I mean, it does require some hand-holding on our part, to be completely honest, right? I mean, that's why maybe I wasn't really trying to downplay it, but maybe that's why it came across that way.
I think all DPUs are going to need some handholding.
Yeah. Ours, ours will need some handholding. Yeah, fair enough. Thank you. Yeah. Yeah.
It's not digging on you at all.
Yeah. Okay. Thank you. Yeah. Okay. Got it. More questions? Yeah.
Can you talk a bit about the erasure coding and the topologies that are supported? Is it like within an enclosure only, or is it rack-wide?
Yeah, it's actually we have what we call programmable fault domains. So you can tell us when you create a volume, you can say, hey, the fault domain is a rack, in which case we will spread that erasure coding across our boxes. So for 4+2, we would make sure we would find 6 units in 6 different racks and make sure that they are spread across. On the other hand, you could also tell us that, hey, we've had some customers who will tell us, my racks have never failed. I don't care about rack level, in which case we'll do 4+2, but across 6 boxes, and they can be within the same rack. For the longest time, that was the only form of erasure coding we did. We didn't do anything inside the box. We just said, for boxes can fail, we've got to be able to protect against it. So the standard form of erasure coding we do is across the networks, in answer to your question now.
And it works with the standard Linux NVMe TCP driver?
Absolutely does, yeah. And has been for 2 years now.
Where a single volume is sort of spread across a number of boxes?
Absolutely, yeah. Yeah, it does work.
The Linux is only one box, but not one. If there is a master node, several nodes behind.
Yeah, there is a notion of a master that you talk to, and then that guy talks to the other DPUs and so on. So, but yeah, it does totally works.
Is not only going through primary at any given point in time?
Yeah.
Just on top, I think there was a node that had all the database map.
Yeah, that's the thing. We sometimes call it the control plane. Sometimes we call it the composer. I think his talk, he called it the composer. Yeah. So we have that. If I go back to my picture here, go back far enough. Yeah. So you can see those 3 boxes up there. That's where the stuff that Jaspal was talking about is running. We have separated the control plane. That's got a REST API, and you can either program directly to the REST API, but we've already built Kubernetes and OpenStack plugins. So for a lot of customers, they don't have to muck with that. We just give you a CSI plugin if you're in Kubernetes. It talks through there to create volumes, delete volumes, create snapshots. All of that is through that control plane.
So standard for software was used to contact the composer node creator, download the basement map, and then talk directly to the
So these guys don't need to, the servers on the left don't need to contact the composer nodes to get placement maps or anything. There's a create volume call that comes into that composer node. Then that composer node decides sort of like, which volumes that might get spread to. Then there's a notion of a primary, if it's spread across, as he was asking. If it's spread across, there's a notion of a primary. And then, when you do the connect all kind of command from here, you go to the primary you set up your device driver to have like one guy is the preferred path and there's this other path for failover and so on. Yeah, exactly. So on the right, it'll go to the primary. The primary, in our case, we keep collecting things into an NVDIM, just enough big chunks, and then at some point we shard it, break it up into 4 or 5 pieces, send it all to the other guys, and so on. Yeah.
Metadata associated
The composer, I think of it as a two-level map. You know, think of the composer as having a high-level map of things, and then within the storage boxes themselves, there's sort of lower-level details. So it's kind of a two. Correct. Yes. Yeah, we have automatic failover. You'll go to a secondary node. If you can't reach the primary node, you'll go to the backup node. A new master can be elected. That guy becomes that guy becomes the new master for that volume, and a secondary is elected, and so on. So everything is always continuous all the time. So if all three composer nodes go down, by the way, we're not limited to three, okay? I mean, you can if you're not happy and you think three can go down, put five. You know, I mean that's a cluster, right? That's a cluster. But yeah, if all three go down and the control plane is completely inaccessible, you can still continue doing reads and writes to volumes you have created before, but you don't have the ability to create new volumes until those nodes come back up, or you build them back up. And we have a backup of the Cassandra database that we can bring back and things like that as well. So we have backups on backups to make sure that.
Within the data plane, any failures, like let's say RAID failures, disk failure, all of those are handled?
All of those are handled, yeah. Correct, yeah. I'm out of time, she tells me, but people are interested. I'm happy to keep answering questions. I don't know whether there's anything else you guys need to go to, but.
If there is a node failure, do you fail over the IP, or it is up to the host to connect to the other TV?
The host driver will connect using, we'll have the secondary IP to go to, yeah.
But you don't fail over the IP?
No.
So the multipassing software on the host feature, it knows both of us. It's connected to both of them. Always connected to both of us. So each of the two are you having its own IP address?
Yeah, there are multiple IP addresses per 2U, but now we're getting into more details. But there's a BMC IP, and then there's really two DPUs in there, so each DPU has its own IP, things like that. But. Yeah.
Another question, you've shown that you've got 4 or 800 gigabit pipelines coming in, right? Ports coming in.
Each DPU, yeah.
Right?
Yeah.
And then you showed that you've got 2 DDR4 memory channels.
Yeah.
Right? So, wondering how are those 2 memory bandwidths balanced? Like you only have 2 DDR.
Yeah, well, we have an HBM. We have high bandwidth memory. I mean, a lot of the buffer payload stuff goes into HBM, and all the, compress the data, take it out, encrypt the data, that's all going to the, we've got 4 terabits per second of bandwidth to the HBM. That's what really gives us the performance. Yeah.
The DRAM is mainly used for the DRAM is mainly used for
What is mainly used for? Sorry.
the DRAM.
The DRAM is
Mainly used for
how big is the buffer memory?
How big? Sorry,
How big is the buffer memory?
it can go up to half a terabyte to a terabyte. So it's plenty of buffer memory.
For the FS1600, how many network ports do you have for the data part?
For the each one of those guys has 8 100 gig links coming out of it. So I need 800 gig ports somewhere in your torus.
And they're all active.
Yeah. We do bonding. I mean, 4 of them get bonded. Yeah.
So you've got the memory that you have DDR4, but then you've got NVDIMM.
We have NVDIMM.
You play a little bit on the flow, like
So the NVDIMM is for fast writes, essentially. The NVDIMM is essentially for fast writes. Data comes in, We make one copy in one NVDIMM, we make another copy in a second NVDIMM on a second box, and then we tell the host, your write is done. So that's for effectively fast write purposes. The HBM is for all the flow of data, all these, data comes in, compressed, encrypted, that most, and then regular memory, for state and other things, right? Well, we also have these, essentially we're doing virtualization, right? We're doing a log structured write. The write is not going back in place, right? Things get accumulated. I'm taking random writes, I'm putting them into NVDIMM, and then I'm making sequential writes. So data is never going back in place. It's a log structured write design. You need a table somewhere to say, okay, block X is now sitting where? So all that is in DRAM, right? That block table, block map table, if you will, that's in DRAM. That you need a bunch of RAM to hold the block map table. So that'll, yeah. Yeah, yeah.
You have a floating point support?
Yeah, yeah, the DPU does have floating point support. I think the F1 can do 1.6 million floating point operations per second or something like that. So it is available. I don't know that we use it very much, but but it's there. What else? Have I worn you out? All right. Thank you very much.